Hi guys. So continuing from where we stopped last class on chapter 10, um, basically now I'm gonna show you how to do the analysis of proportions in that specific case where we have more than one sample, and how to perform the hypothesis test. I'm gonna show you one example and some other details, but I just wanted to go back one slide to show you to just discuss actually one more thing about uh, the case when you have the standard deviation from the population is unknown in your problem. Um, in general, and I think I told you at some point or in a few points during our class that we have a sample size that's sort of ideal for statistical inference, or at least recommended to statistical inference, which is when you have a sample larger than 30 units or 30 observations. Um, the specific case that the standard deviation of the population is unknown is a case mostly applied when you have less than 30 units on the observation, and then you need to perform the t-test. But what I'm trying to say is that the t-test is most useful when we have small samples or small sample size. Uh, in general, that's the information that you have from the exercise that will help you to detect if you need to use the t-test or not. So if you see in the exercise any information about that sample size is 5, or we have a sample size that's smaller than 30 units, uh, you need to immediately think that you need to use the t-test instead of the z-test. Um, I'm saying that because sometimes in the exercise you don't have the information that the standard deviation is unknown, but instead you can have the size of the sample, and that size of the sample reveals to you that you need to deal with you need to perform the hypothesis test using the t-test, not the z-test. Okay. Um, so I think that what I want to highlight here in this point. So pay attention in the sample size information in the exercises, because that could reveal to you what type of test to use. Okay, I already presented to you. Here we need to make the assumption that I told you in the last minutes of the class. If we make that assumption that the standard deviation of the sample is equal to the standard deviation of the population, basically we can use the degrees of freedom formula that's in the end of this slide right here. Okay. If not, we need to use the correction term, which I just showed you is in the note of this slide, and it's in the book as well. Okay. The information for that is basically making the assumption and if the assumption holds or not. But as I told you, most of the time you're going to apply the standard version where the assumption holds, and you need to calculate the degree of freedom with the formula number of observations of the sample 1 plus the number of observations in the sample 2 minus 2. Okay. I'm going to skip this exercise because we already have done this exercise in class, and I'm going to go right to proportions, which is our sort of third case. And again, this case is exactly the same as the cases that we had before. The difference is that we have now proportions from 2 samples instead of just 1 sample and 1 population. We can denote the proportions of different samples as P1 and P2, as we denote the averages of the different samples by X bar 1 and X bar 2. Basically, what we are interested in testing here is the difference between the 2 samples, if they are equal or not, and the information that we had from the previous tests with 2 samples is also valid in this case. basically testing the difference between the two samples. We are trying to understand if those two samples are coming from the same population or not. We're going to have the same D term here. So the D is the target that you are trying to test. Most part of the time, D is going to be equal 0, meaning that we are testing if the two samples are coming from the same population. Okay. P1 minus P2 is actually the random variable that we are trying to estimate now, which is the difference between the proportions of the two samples. Okay. Remember, the proportion is given to you by a categorical variable that define a group inside of the sample. So that could be gender, that could be, in the case of our study case, we analyze defective orders, that could be in other groups, like we can create division of groups of observations by ethnicity, for example, or any other categories that they may have that help them to identify themselves. And then each proportion of one category inside of this group is what we are analyzing and we are calling P. Basically, the proportion is given to you by the number of observations inside of this smaller group inside of the sample divided by the total number of observations in the sample. Okay. We have the same idea that we had before. This first identity should hold, which means that the expectation of the difference of the two proportions from the population should be equal, from the sample should be equal the proportions of the population. Note here the difference is that we changed X from P, and P bar are the proportions of the sample always as X bar, and P are the proportions of the population. Okay. The standard deviation of the difference of the proportions is given by, same as we had before, basically because the proportions are defined by a categorical variable that is generated given a binomial process. The first term in the numerator here is the binomial variance, as we saw before, divided by the number of units in the sample one. The difference here is that now we have two terms, one for each one of the samples. And basically the notation of the subscripts determine which sample we are dealing in each term, right? So the first term is the proportion for the sample one, the second term is the proportion from the sample two, and the numerator is then the number of observations in the sample one, and the numerator in the second case is the number of observations in the sample two. So the unique difference is that previously we didn't have this second term right here. We just have this one term right here. And the standard deviation was calculated again as the square root of this term, which was the variance divided by the number of observations. Okay? So the difference that we have here is the addition of the second term, basically. What we can do with that is the same process that we've been doing for the samples as well. We can invoke the central limit theorem and say that if the sample size is sufficiently large and we have a sample distribution of the difference of the proportions, that distribution will be normally distributed. And basically we can expect that we have a standard error that gives us the length of the distribution in this case right here, and how the distribution is going to be shaped, if the distribution is going to be more wide or more concentrated, is going to depend on this standard error. Okay, here this standard error term is defined basically as we just saw in the previous formula. And the standard distribution, we can then standardize this normal distribution from to a standard scale, which varies between 0 and 1, meaning that the average between the line is 1 in this case, or the average below the line is 1. And in what's different from the previous distributions is that instead of being centered at the average of the sample, the standard distribution in this case is centered at the difference of the proportions of the population, okay, or the proportions of the sample. The x-axis in this case is given by standard deviations from the difference of the average difference of the proportions. So how many standard deviations we are from the middle here, which is the average of the proportion, from the positive side or the negative side. Everything's the same. The concepts are all the same. The basic difference that we have is that additional term in the formula of the standard error, which is a replication of the first term that we had. We have slightly differences when it comes to the hypothesis test, and the differences in this case are highlighted in red in this slide. I would say the main difference here, which is not new as well, because we saw that for the averages, is that because we have a proportion, and that proportion may or may not be equal of the proportion of the population, and we have some uncertainty around that because we don't know clearly the population when we have more samples. Is that what we are actually testing? To define the hypothesis tests, we need to make an assumption, right? And that assumption also helps us to define statistics from the sample that helps us to calculate the z-score and the z-calculated to perform the hypothesis test. Okay. The assumption behind of that is that the proportion of the sample 1 is equal to the proportion of the sample 2, and they both are equal to the proportion of the population. That allows us to, instead of having the proportion of the population that we don't have any information, is the same as from the standard deviation of the population, when in the case that we don't know the standard deviation of the population, in this case we don't know what is the proportion of the population, we can instead make this assumption and then calculate the proportion of the samples, which is a pooled proportion of the samples because we have more than one sample, and use that proportion p bar to calculate the standard error, the standard deviation, and then to calculate this. Okay. So basically you calculate this pooled version of the proportion by weighting the proportion of the sample 1 by the number of, multiplying that by the number of observations in the sample 1, plus the number of observations in the sample 2 times the proportion in the sample 2, divided by the number of observations in the sample 1 plus the number of observations in the sample 2. Note that this is pretty similar to what we have done with the average, with axis. And this is basically a weighted average of the proportions of the two samples, right? And this weighted average is basically weighted by the number of observations in each sample, okay? You can think about that as being the pooled number of successes in the numerator divided by the pooled sample size, okay? So it's the number of successes in the first sample plus the number of successes in the second sample divided by the summation of the two samples. Basically, let's give you an example to make it more clear. So you have let's say that the categorical variable that is defining the proportion is gender. So we have let's say boys and girls, in the two samples. And the proportion in this specific case, let's use it as an example, we are analyzing is boys, okay? So we are basically looking for the number of boys divided by the total number of observations in the sample 1, and the number of boys in the sample 2 divided by the total number of observations in the sample 2, okay? That's the idea behind of this formula. Basically, what is additional to that, what I'm telling you is that you are weighting the proportion of boys in the two cases in the numerator here by the number of observations that you have. Okay? So this, we can call that as a weighted average. After you have done that and you have calculated P bar, you can then use P bar to calculate the standard deviation of the differences of the proportions from the two samples. You don't need to apply P1 and P2 anymore. You can simply use this weighted average in the formula, which is basically the same formula as we saw before. Okay, but instead of having P1 and P2, now we have just P. Okay, this formula is exactly the same as this one. Note that the difference is that this is just a mathematically more elegant way to separate the terms and leave the fractions here in one specific term, but the formula is exactly the same. So if you multiply that, the multiplication is going to be linear, right? So you're going to multiply this whole term by 1. So you're going to have this term right here on the top of this first fraction. And if you multiply this second term, you're going to have this exactly term on the top of the second fraction, which is going to be exactly as this. The difference is that you don't have P1 and P2 anymore. You have P bar, which is the calculated, weighted or pooled proportion that you just did. Okay. Then we can proceed basically calculating the Z statistic. What we're going to do in the Z statistic is you're going to use the average proportion of the sample 1 minus the average proportion of the sample 2, which is the difference that we are estimating, divided by this standard error right here. Okay, so then you can find Z. Basically, because of this assumption, we are assuming that the proportions are normally distributed, so the difference between the proportions should be normally distributed as well, as I told you in the previous slide. Then what we can do is basically compare that Z calculated with the Z based on the alpha that we are defining, or the confidence interval that we are defining. Okay, so this is the way that you're going to calculate Z, as exactly same as you were doing, for example, from T, right? So you have here the calculation of T, and exactly the same as you were doing from Z. Okay. Okay. One thing that's slightly different is that D is not necessarily present here, because you don't need to define targeted populations for this specific case, or target proportions from this specific case. So because the proportions are defined by a binomial process, so once you categorize like the number of successes that you have in one sample, and the number of successes you have in the other sample, you don't need to create any other category or target to compare if they are from the same population or not. You just need the difference of the proportion. Okay. Because of that, we don't have V here as we had previously in the forms. One thing is the setup of the test of the hypothesis in this case. They are essentially the same. So you have the two-tailed hypothesis always defined by the alternative hypothesis. If you have a equality, as I already told you, you have a two-tailed hypothesis. If you have inequality in the alternative hypothesis, you are dealing with a left-tailed or right-tailed. I think that's something that I didn't told you, but note that is sort of intuitive to note that if you have a hypothesis test in the if you have defined your alternative hypothesis as being greater, you have a right tail test, and if you have that as being less than, you have a left tail test. Okay, so this means what is the side of the tail that you are selecting your test, basically. Remember that left-tailed and right-tailed, you're going to use the single-tailed table, and the two-tailed, you're going to use the two-tailed table. Okay. I think some of you asked me about what happens if I have a z-score that's negative. You can still use this, especially I think if that's happening in the two-tailed case, you have the negative and the positive side, so that's not a problem at all. If that happens when you have a single-tailed test, what you can do is basically, depending on the test that you are doing, if you are not finding the table, you can use just the absolute values to find that in the table. Why is that? Because independently if you are doing a two-tailed or a single-tailed, the distribution is symmetric. So once you find one value that's positive, the negative side of that distribution, if that exists in the case, would be the exactly same z value that you found, but negative. Or if you find the negative version, the positive would be exactly the same value as well. So this symmetry of the distribution as a characteristic gives us this possibility. So you can basically just look for the absolute values. You should be fine. Let me move to the next. So here's one exercise for proportions. Basically, we have a company that's conducting a test to evaluate the effectiveness of clients. How effective is one marketing campaign from groups of clients? Is that the idea? Before they have a new campaign available, they did a survey with some households. So this number of households, for example, those are the things that I think I wanted you to note when you are reading an exercise, for example, to extract information from the exercise. Is basically, in this case, I'm specifying the number of households, meaning that's the size of the sample that we survey. So you need to associate that's n, for example, in this. Okay. And for example, dealing with proportions, we are looking for the number of successes, right? So the exercise is also giving you some categories that would allow you to make a distinction between successes and failures. So in this case, is the number of households that's aware of the product. Basically, this is the proportion of the sample that you are looking for. So this number divided by the size of the sample that you already have here is the actual percentual proportion or is the percentage number of the group that has the category that you desire, or success in this case, right? Um, so they give you a second case where they started the new campaign, and then they asked, they did a new survey with a different size of N, and how many people were aware of that as well. Okay, and he's asking you based on this level of significance, meaning that you have 95% of confidence in this case and 0.05 of significance. Every time that you see significance, you have it already defined your alpha, right? So this is your alpha. Um, and then he's asking you, how can you define the proportion in this case with this level of significance, okay? The test that we can do then is compare the two samples that we have, the proportions, and see if the difference of the proportions are less or equal zero, which is the status quo hypothesis, or the null hypothesis in this case. Okay, we are saying they are not different from each other and they are probably being drawn from the same population. In the second case, we want to know which is the alternative hypothesis, if they are actually different from each other and probably being drawn from different populations. Okay, meaning that if they are being drawn from different populations, the proportions of 1 and 2 should be different. Well, then we can apply the knowledge that we had before. What we can do is basically evoke the central limit theorem, understand that this difference is creating a normal distribution given a sample size. As I told you, for example, 30 observations is a statistically fine number to define statistics with some power, with some confidence power, based on the information that you have in each one of the sample. For each one of the samples, you can observe that we can then perform a z-test in this case. If you have just few observations, you could perform a t-test as well. But in this case, we have enough observations, more than 30, which gives us the opportunity to just run a z-test as we have done regularly. In this case, the z-score can be calculated by this formula, which is basically in the numerator, the difference between the proportions of the average. What you need to do for calculating the second term, you need to calculate the pooled proportion sample, which is basically the formula in red here, which is the weighted average of the two proportions of the two samples. Let me just move this right here. So if you do that, you're gonna end up with 0.408, 48. And then what you can do is just apply, or you can just apply in this formula right here, substituting P bar from this P bar. Sorry, I think here is 0.45, no, 0.48. Okay, 0.48 is basically if you divide each one of the proportions and just sum the two of them, you calculate 0.48, but if you do the weighted average, it's 0.45. Basically, then you can perform the calculation of the z, right? And you can also go to the table and perform the and find what is the z associated to 0.05 level of significance. What you do in this case, you do basically the same process that you have done before, which is, you know, the level of significance. You go to the table and you look for this level of significance, and you're going to find what is the z-score associated to it. And you're going to compare the z calculated here that we just calculated with the z that you find in the table. Basically, you can find this in different notation, but basically z alpha, because we have a single tail test. If we have a two tail test, that would be z alpha divided by 2. And this z right here is the z that we just calculated here. Okay. In this case, what happened is that the z alpha is greater than z. So we fail to reject the null hypothesis, and we cannot say that the campaign had increased awareness in the samples that we analyzed. Okay? Meaning that they are essentially different samples. We are, in this case, supporting the null hypothesis. And they are probably being drawn for different populations. Okay. I think this is a very important slide. I think, as I told you in chapter 9, we have a summary of all the formulas. This is the slide that you have the summary of all the formulas. Basically, from when you are dealing with the sample means, and you have, in this case, more than one sample, and you have two cases that you can analyze in the sample means from more than one sample, when you have the standard deviation of the population given to you or no, and when you have the standard deviation of the population unknown. Okay. In the first case, you're going to use the z formula regularly. The difference from the z formula, as I told you, is basically this term d right here, which is the target that you are trying to analyze. Most of the time, d is going to be 0, and that you have, instead of just x bar minus mu here, you have x bar minus d0, and you have one additional term in your standard error in the denominator, which is basically the same as the previous term that we just have when we have one sample, basically for the second sample now. Okay. When we have the case that the standard deviation of the population is unknown, we basically need to make one assumption, and that assumption is that the standard deviation of the samples will be equal to the standard deviation of the population. If that assumption holds, then we can calculate the pooled version of the standard deviation from the two samples, which is given by this formula. And using this pooled standard deviation, we can then calculate the t statistic and use the t table in this case to the analysis. Remember, for that, when you make the assumption, you need to calculate the degrees of freedom that you have to find the t score. And if the assumption holds, you can calculate the degrees of freedom by number of observations in sample 1 plus the number of observations in sample 2 minus 2. The third case is the one that I just presented to you. Is basically we can perform a z-test again. We can calculate the z-score using this formula. and this case is applied when you are looking for the difference of the proportions. Again, we have a case where the uh, the proportion of the population is unknown. We need to make that assumption that the proportion of the sample is going to be equal to the proportion of the population. If that hypothesis hold, or if that assumption holds, what you can do is basically calculate the pooled version of the proportion, which is given by this formula. And you're going to apply this pooled version in the calculation of the z. Okay. What you have more here now in the hypothesis testing is basically you need to define those assumptions, right? And then calculate these additional pooled or weighted average for those two cases. Okay? Again, the formulas are a little bit bigger and scarier than before. So, but at the same time, they have this basically the same terms and all the terms are given. So don't worry too much about that. Always remember that everything that has a bar refers to the sample. If that is X, we are talking about means. If that is P, we are talking about proportions. N is going to be always the number of observation. And the subscript now is determining whether is this number of observation from the sample 1 or from the sample 2. Could be sample 3, 4, or 5. What happens if we have more samples? Basically, you increase the number of terms that you have in the denominator and in the numerator of the formula. So the difference would be x1 minus x2 minus x3, and in the denominator would be psi1, psi2, psi3, and 1 and 2 and 3 and so on. Okay? But the formula is still the same. It's just you add more components from the additional samples that you. This table is very important. I'm going to leave this slide from you in the exam as well. So this table is actually showing the values that you need, the z-score for each one of the levels of significance that you have, 0.01, 0.05, 0.001, 0.05, and 10%, which is 0.1. And what is the z-score in each one of the cases? From the two-tailed, single-tailed to the right, single-tailed to the left. So you don't need to necessarily go to the tables and look for these values. You just need to identify what is the alpha that you are dealing with and just come here and grab the value. So what I'm telling you is that given that you have access to the slide during the exam, if you are asked to perform a hypothesis test, you don't necessarily need to search in the Z table or in the T table. You can just use the slide, for example. Okay, good tip. This is going to be the code for this class. So if you are watching the class, please enter in the class from the day and post the form as soon as you watch the class. The time the form that will be available is going to be exactly the same time of the class. So please do that. I'm going to send that in the announcement as well, but you can just figure out the code after watching the video. If you have any questions or considerations about the exam, please send me an email. I won't hold any office hours tomorrow, which is the day of our class. I'm recording the video on Wednesday. But if you have any questions that I can answer by email, please let me know. Or maybe if you have something that's a pressing concern that you need to talk, please let me know. I may be able to set up a time, 5-10 minutes in a Zoom meeting that we can talk. Okay, see you next week for the exam. And I would give you some advice of read the chapters again and explore especially examples and tryouts from performing hypothesis tests and creating confidence intervals and analyzing confidence intervals, the interpretations using confidence intervals. I think those are the most important topics that you need to know to perform all these steps. So you need to be very familiar with the formulas. There is no other way around of being familiar with the formulas than repeating the exercises, or at least one exercise many times. That will give you the chance to absorb not just the components of the formula, but also the mechanics of performing the test and understanding what all the steps are. Okay? I think that's it. If you have any questions, please let me know.